Good evening, everybody. Welcome to the Royal Society. I'm Alex Halliday, the Physical Secretary and Vice President of the Royal Society. I'm also a geoscientist, so tonight's a particular pleasure. We've got Matt King, Professor Matt King from the University of Tasmania here to present a lecture, the Kavli Lecture, entitled Continental Loss, the Quest to Determine Antarctica's Contribution to Sea Level Change. And I'm just going to go through a few things that you need to know before we just get started. The first thing is, please can you switch off your mobile phones if you've got them with you, or at least switch them to airplane mode or something like that. There are no planned evacuations, so if you hear an alarm, it's probably real. So just to sort of point out to you that there's an emergency exit here, over here, and then there are exits out the back as well if you're closer to that area next to the dining room. If anyone has any access needs, just let us know, and there'll be people around to help the members of staff. The event is being webcast, which is something we've started doing quite a lot of just recently, and recorded. So your questions will be recorded as well as part of that towards the end. At the end, also, I think you've been given a questionnaire to fill in, just to give us some feedback on how you think we're doing as a society. If you could fill that in, that would be really helpful, and hand it in at the end. There should be, if you haven't got one, there should be some at the table outside the door. So let me just introduce to you a little bit about the Kavli lecture. The Royal Society Kavli Medals were established in 2010 in recognition of the Kavli Foundation's generous donation towards the Kavli Royal Society Centre at Chicheley Hall, which is up near Milton Keynes. The Kavli Education Medal and the Kavli Medal and Lecture are awarded annually in rotation to individuals who have made a significant impact on science or mathematics education within the UK, and for excellence in all fields of science and engineering relevant to the environment or energy. The first Kavli Medal and Lecture was given in 2011. The lectureship is accompanied by a medal and a gift of £500. Now let's say a little bit about tonight's speaker. Professor Matt King was awarded the Kavli Medal and Lecture for his research in field glaciology, leading to the first reconciled estimates of ice sheet contribution to sea level. Matt King grew up in Tasmania, Australia, where he first developed an interest in Antarctica, and in particular in using precise measurements to understand how its ice sheet has changed and is changing today. He completed his PhD on this topic at the University of Tasmania, and then moved to the University of Newcastle upon Tyne in the UK, where he researched GPS positioning and its application to understanding glacier dynamics, Earth deformation, and Antarctica's contribution to recent sea level change. He has travelled to both Antarctica and Greenland, and in 2012 he joined the team that produced the first reconciled estimate of ice sheet contribution to sea level change. He is now located back at the University of Tasmania as Professor of Polar Geodesy. Matt has been recognised by a number of organisations, scientific organisations around the world, including the American Geophysical Union, and it's a great pleasure to welcome him tonight. Matt King.
Well, thank you for coming along, and thank you, Alex, for that introduction. It would be a lonely experience without you, so I'm particularly glad that you're actually here tonight. I want to thank a few other people. This is a photograph of Fred Kavli, and I want to honour his legacy and generosity to science and engineering throughout his life. And also thank you to the Royal Society for giving me this great honour of speaking here with you tonight. I've spent all of my career at two institutions, Newcastle University for 11 happy years in the northeast of England, and I want to particularly thank Peter Clark, who nominated me for this prize. And before that I was at the University of Tasmania, and now again, and I just want to acknowledge the fantastic colleagues I have there that I work with. But we're here tonight to understand the fate of a piece of ice. Now it may not be a small ice cube like this one, but nonetheless this ice cube has something very much in common with the Antarctic ice sheet, in that it's responding to its environment, that it's around it. It's responding to the air temperature, and if this plate or cup was full of water and that water was in contact with the ice, it would be responding to the temperature of that water as well. And we're interested in the fate of the Antarctic ice sheet, more so than the fate of these ice cubes, because of sea level. This is a series of data from covering the period 1700 to 2010. The solid lines, use the mouse pointer here, these ones here, the pink and the blue and whatever colour that is, are reconstructions of sea level based on tide gauges around the globe. The dots are independent reconstructions based on salt marsh studies, again from around the globe. And then for the most recent period from about 1993 onwards, the red line is measurements of sea level from satellites, from satellite altimetry. And so you can see there are a number of things. For the period up until about 1800, 1850, we see not much has been going on with sea level. In fact, you could go back several thousand years and you would see that it didn't deviate from zero by much more than 10 centimetres, 20 centimetres. And then since about 1850, around the time of the Industrial Revolution, we see the sea level rise take off and dramatically increase to an average over the 20th century of about 1.7 millimetres a year, or fractionally lower. And then during the most recent period, and I'll zoom in on that, this is the satellite altimetry record, we have a rate of not 1.8 millimetres a year, but 3.2 millimetres a year. So we see there's been a dramatic increase, and there's some bumps and squiggles in this time series, but there is no doubt that there has been unabated sea level rise at a much higher rate in the last 2 decades than in the century beforehand. So that leads us to the question, well, what's driving that change? What is driving sea level change? And that leads us to the question of, well, how do we measure things like the Antarctic ice sheet? How do we measure the change of something as vast as twice the size of Australia, or a bit larger than the continental North America? If it was only a 1 centimetre iceberg or ice sheet, that would be a relatively easy thing that most of us, I think, could actually achieve tonight. But Antarctica is much bigger than that, and it's much harder to measure. And just before I go on to discuss how we actually measure ice sheet change, I just wanted to clarify something. The iceberg on the left is floating in the ocean, and when it melts, it won't change sea level more than a tiny fraction. The ice cubes on the right, when they melt, that water will flow away and into the ocean, let's say. And that would change sea level. And the difference between them, of course, is the one on the right is grounded above sea level. It is resting on something. It is not floating in the ocean. And so I'm going to be talking about the ice sheet, the Antarctic ice sheet, that is grounded, the one that is sitting on rock, not the one that is floating around, the Antarctic ice sheet, which has a climate signal very much of its own, but when it melts and freezes on a cyclical basis or changes over longer periods of time, doesn't have a direct effect on sea level change itself. The one on the right most definitely does, and that's why we're interested in that in particular. I guess this photograph is the sort of thing that you used to be able to do in Antarctica, but you can't do anymore. You can't do this anywhere, really. Starting in the 1950s, scientists set off on great endeavours across the Antarctic ice sheet in order to understand it, using geophysical techniques. They wanted to measure how fast it was flowing. They wanted to measure how deep the ice was. They wanted to measure if it was melting. They wanted to understand how icebergs carve off. They wanted to understand everything there was about it. But despite their best intentions, there was no way that a group of people moving across in skidoos or even in aircraft were ever going to measure the Antarctic ice sheet in its completeness, and especially the change in the Antarctic ice sheet over time. And so fortunately, starting in the 1990s mainly, satellites were launched. Some of them launched specifically to study Antarctica, some of them for other reasons, but including Antarctica. And now we have an array of wonderful tools where we can actually begin to study and understand the Antarctic ice sheet. That still hasn't answered exactly how do you measure an Antarctic ice sheet? How do you measure the change of the ice sheet? And there's an analogy to how you measure a changing audience size. I'll say tonight that you are a much more attractive audience than this one here. But the question is, how do you measure a changing audience size? Well, you can count the number of people who come in, count the number of people who go out. Hopefully tonight that most of you will stay to the end, at least out of politeness. And the difference between those two things will be a changing audience size, as you know. And if everyone lines up very politely, as some countries are prone to do very well, and if nobody leaves like this, then we'll be in pretty good shape. The second way that you can measure a changing audience size would be to measure its volume change. So we can measure the volume of this room and the height of this room. And as that changed, then we could get some sort of inference on the change in the audience size from that. And here I've represented you, and I hope you're not offended by a field of lettuces viewed from above. And the third way to measure a changing audience would be to weigh the room, if we could put a giant set of scales beneath this room. And as the weight of the room changed, we could get an indication that the audience size was changing as well. And so we have three approaches: an input minus output approach, a volume change approach, and a weight change approach. And all being well, those things would equate with one another. We could count that in those three different ways, and they should all add up as well. And so the same thing can be said about the Antarctic ice sheet. We can adopt that same set of approaches: the snow in minus the ice that flows out. And so we can take meteorological models of the accumulation of snow in Antarctica, and that will give us an estimate of the snow that's entering into the continent. Now we know that even predicting snowfall in Britain is difficult and challenging, and that's quite a well-observed place, let alone Antarctica, which is vast and very poorly observed. So this is by no means a certain exercise. And then we have the ability to measure snow. Oh, sorry. What's going on there? Measure the velocity of the ice sheet. And this is a wonderful data set. This is not models. This is not computer animation. These are actually observations derived from satellite products where the velocity of the ice sheet has been tracked in painstaking fashion with vast amounts of data. And we can see the rivers of ice forming at the interior of the ice sheet and flowing out towards the external edges where it discharges across the grounding line, as it's called, where it becomes a float, and there it begins to affect sea level. But we need to know more than just how fast it's flowing, because we want to know the mass of ice that's flowing out. And so we need to know the change in velocity with depth. And this is one of the very poorly understood things. We can measure the surface, the upper surface, its velocity from space. But how does it actually vary with depth? And there's some assumptions generally required in order to get that information. And then we need to know exactly how thick the ice is when it starts to leave the continent and becomes afloat. That's the third part of the volume equation. And here we have had, for many years, many decades indeed, airborne radar penetrating through the ice column, bouncing off the bedrock below it and returning to the aircraft, and enabling geophysicists to determine the elevation of the bedrock right throughout Antarctica, revealing all this wonderful detail right through these areas here. In some areas we see that doesn't appear to be much detail, and over here as well, and that's because there actually is very little data in those regions, one of a few regions which have been very poorly sampled, not because there's no actual surface features there. But nonetheless, in the areas around the coastline, we're able to now say, well, we know what the depth of the ice is. We know the depth of the bedrock, we know what the ice surface is, so we know what the height of the ice is. So we know its velocity, we know its height, we know the width of the glaciers, we have an estimate of how that varies with depth, and so that tells us the mass of ice that is leaving Antarctica. And so from the snowfall in minus the ice out, you can produce estimates, you can difference those two, and produce estimates that are like this, that point to areas of West Antarctica that are losing substantial mass. I'll return to the details of this later on. This is just to illustrate that these areas are pinpointed by this technique. And in this estimate, at least, very little of the rest of Antarctica is changing. So that's the first approach. Then we have the second approach. Let's measure the volume change of the ice sheet and the density of that change. And here we again have satellites that measure by laser or by radar the surface elevation of the ice sheet. If you can position the satellite to an accuracy of a few centimetres, like we can do now with very precise geodesy. Then you know where the satellite is. If you measure the range from the satellite down to the surface of the ice, then you know the elevation of the ice. Over a period of time, you can map that, and you can see the ice lowering or indeed rising, as it may be in some cases. And so you can produce maps of ice volume change like this one, again highlighting this, highlighting this area of the West Antarctic ice sheet, which seems to be changing quite dramatically. Here we're seeing glaciers that are many tens of kilometres wide, 100 kilometres long, that are thinning half a metre a year, 1.5 metres a year, even more. And then we see other areas where things are changing. You know, here we have this area where there's ice elevation increase because this glacier stopped flowing 150 years ago. So it's just snowing and snowing and snowing, and there's no discharge at all from that area. And then we have the third approach, which is weighing an ice sheet. And here in 2003, NASA and the German Space Agency combined together to launch the Gravity Recovery and Climate Experiment. And this is a wonderful tool because it measures the Earth's gravity field. So this is the GRACE mission. It's actually 2 satellites orbiting the Earth about 200 kilometres apart. And GRACE is measuring the inter-satellite distance, so the distance between those 2 satellites, to about a 50th of a human hair. And it's measuring that distance so precisely, 200 kilometres, because the distance between those 2 satellites changes based on the mass that is below each of the satellites. So for instance, as the lead satellite approaches a mountain range, the gravitational attraction to that satellite, to that mountain range, is greater for the lead satellite than the hind satellite. And so the distance between those 2 satellites expands out. And then it continues to vary as it travels over the surface of the Earth. Month after month, we can produce maps that reveal changes in the ice surface or changes in mass around the Earth. And so we can track, using this slinky-like satellite, if you like, the mass changes on the Earth. And here's a map, just for illustration, of the sorts of pictures that you can produce that give us an idea of mass changes that are going on in the Antarctic ice sheet at relatively low spatial scales here, about 300 kilometres. So not picking out individual glaciers, but actually generating a product that is all about mass, which makes it really quite unique and a wonderful tool. The trouble with GRACE is that it doesn't measure ice mass. It would be great if it did, but it actually measures total mass. It measures mass changes in the atmosphere, mass changes in the solid Earth, mass changes in the ocean, hydrology, and as well as cryosphere. And so if we want to get at the cryosphere, so the ice change, we have to take the measurement from GRACE and subtract away the atmospheric change, the ocean change, the hydrology, and the change in the solid Earth. And if we can't do that well, then our estimates of cryospheric change, ice change, will be compromised in some way. But all things being well, if we weigh the change in an ice sheet, if we measure the input minus the output, if we measure the volume and the density, then those things would be in agreement. So how are we going? And I'm going to show you a series of boxes that look like this. And this is going to be the status as of about 2010. The width of these boxes is going to reflect the time span of the data that's gone into the estimates. The midpoint of the box is going to show us the estimate of the change, and the height of the boxes is going to tell us something about the estimated uncertainty in those measurements, and how confident the scientists were in those estimates. And so we're going to express this in terms of mass change or mass balance in gigatons a year. And a gigaton is 1,000 billion kilograms, or a billion tons a year. And so that's the units that we're dealing with. And on the right-hand side, we're going to talk about the equivalent of that spread out across the Earth's oceans in millimetres per year. So let's have a look at the input minus output approach. This is a summary of some of the estimates that were produced some time ago. And what do we see here? We see 3 different estimates from different snapshots in time. We see that there's an estimate that is suggesting negative 100 gigatons a year, but that's increasing over time. So the input into the ocean is increasing with time, heading towards 0.6 millimetres a year over that period of time. But we see there's great uncertainty in these estimates. And that's largely because at this stage, not all the glacier velocities had been sampled, so there was an upscaling that needed to be done. But there was also not all of the ice thickness measurements had been made either. And so there was significant uncertainty in those estimates. But nonetheless, you could take away from that that Antarctica was contributing to sea level, and quite a lot, and increasingly so. Now, if we compare that to the altimetry measurements, then, well, these estimates are, well, in pretty good agreement, really. These are independent estimates. Some of them are using the same data. But they're suggesting the Antarctic ice sheet is perhaps growing slightly or shrinking slightly, but not doing particularly much differently over time. And then if we look at the GRACE estimates, which come from 2003 onwards, a whole series of different estimates for different periods of time, then you would say that there wasn't a lot of agreement amongst those studies. Although with time there did seem to be some sort of increase in the rate, but with very little confidence given that level of variability between the different estimates. So if we put them all together, well, you can take your pick as of 2010. Was it growing? Was it shrinking slightly? Was it shrinking a lot? And was it changing dramatically with time or not? So it was a bit of a mess. So, well, why was it a mess? The NASA and the European Space Agency wanted to know that answer as well, because they've been launching satellite missions in order to understand the reason for that mess, well, the Antarctic contribution to sea level. And so they pulled together a group of scientists from around the world who were looking to, who were all working on this problem. And 26 different institutions, 7 different countries. Here they are. You can see that no expense was spared in producing these photographs of the scientists. But the reason they were pulled together is to work out, well, why were those estimates different? They were measuring exactly the same ice sheet. There is only one Antarctica. They should be measuring the same thing. And they were to work on ways to address those issues in each of the techniques in order, with the hope of being able to reconcile the measurements one day into the future. That was ably led by Professor Andy Shepherd, who's at the University of Leeds, and Dr. Eric Ivans at the NASA Jet Propulsion Laboratory. And in 2012, just 2 years later, this was heralded in the journal Science, a reconciled estimate of ice sheet mass balance. And so within a period of just a couple of years, we've gone from a complete mess to a very prominent statement that those different estimates had been reconciled in some way. And here's the time series that were produced for Antarctica and Greenland as well, the reconciled estimates. So if we look at Antarctica, for starters, not contributing very much in this first period up until about 1996 or so, and then seeming to increase the contribution, and perhaps with a slight acceleration in there as well, although not statistically significant overall. And Greenland's contributing somewhat substantially, and then much more significantly over time, and then the sum of the two producing the equivalent of about 11 millimetres of sea level rise over that entire period. Much more than the small glaciers around the world, by the way, which swamp that figure at present. If we look then at the parts of Antarctica, we see an interesting story, because it's easy to think that Antarctica is melting, and so all of it must be melting. But there's actually very particular regions, as I've shown you in some of those earlier plots, that are really changing quite dramatically. And so we see here East Antarctica, the vast East Antarctic ice sheet, doing very little. And then through some various snowfall anomalies, possibly, increasing in its mass in the last 10 years or so. West Antarctica losing mass, and most definitely losing mass increasingly over time. And the sum of those two producing an estimate where we see a downward trend and possibly an acceleration in that downward trend. So why, or maybe even how, had we taken a mess into a reconciled estimate? Where did that come from, and how had that been achieved? Well, these scientists have been working hard in their individual groups and collaborating together, but one of the things was that there was an increased effort of actually looking at common data periods, and that's obviously important. If you've got something that's changing over time, you need to compare measurement to measurement over a common period. There were improved snowfall models generated, And that's important, obviously, for that input into the input minus output approach. Improve snow compaction models. If you're measuring the elevation of the ice sheet, you need to know the density of the elevation that you're measuring, elevation change that you're measuring. So there were significant improvements there. Dramatically improved ice thickness data, not by improving the data as such, but by actually collecting much more of it around the continent of Antarctica. And then improved models of solid Earth mass change. You remember that the GRACE satellite mission is not just measuring ice mass change, it's measuring the whole Earth system. And the solid Earth was really a critical error source in there, and there was a lot of work that went into that. And then indeed, that's what I'm going to talk to you about now, because that's the thing I've been most intimately involved with in this project and since then as well. And so what I'm going to talk to you about is what happens when you put a piece of ice on the surface of the Earth. So as an ice sheet has grown here on the surface of the Earth, the solid Earth actually responds. It just doesn't sit there. It responds in some way to the weight of that ice sitting on the Earth's surface. And it responds both elastically, instantaneously. As soon as that ice is placed on the surface of the Earth, as soon as a snowflake falls on the Earth responds in some way, and instantaneously so. And then over a longer period of time, we have a viscous response, a flow of something deep within the Earth, of mantle material deep within the Earth, responding to that weight change as well. So here we have the ice weighing down on the surface of the Earth. We have an elastic response, and then we have a flow away from the area of mantle material, producing a subsidence of the area underneath the ice sheet. And then in the far field, maybe in the ocean basins, for instance, the Earth rebounds up as that mantle material flows into that area. And then when there's a deglaciation, so as the ice sheets have melted over the last 20,000 years since the last glacial maximum, we see a reversal of that process. As the ice melts, we see an elastic response and an immediate uplift up. And then over a longer period of time, over decades, centuries, thousands of years, we see a slow rebound due to flow within the mantle. And the ocean basins, likewise, are subsiding in the present day because of this process. And so this is important because GRACE is measuring not just ice mass change, but is measuring the whole Earth system. And so we need to get an idea of exactly what's happening deep within the Earth if we're going to measure what's happening on the surface of the Earth with GRACE. And so to predict this mass change, we need to know two things in detail. We need to know the details of the changing ice load in the past. So how much ice was in various places? How much ice was in North America? How much ice was in Antarctica? How did that change over time? When did it change over time? So we need to know that sort of information. And I'm going to show you an animation here of one reconstruction of the changing Antarctic ice sheet over the last 20,000 years. And having shown you that animation, I'm sure you're now convinced that we know absolutely everything there is to know about the Antarctic ice sheet and how it's changed with time. And I've deceived you terribly in that case, because that is somewhat true in some areas, I'm sure, but the data that is able to constrain that, as I'll go on to show you later, is limited. So not only do we need to know the changing load of the Earth, but we need to of the ice with time, but we need to know how the Earth responds when a load is changed upon it. And here we need to know things about the structure of the Earth and how it behaves differently at different depths within the Earth. And without accurate knowledge of both of those, of the ice load and how it's changed with time, and how the Earth responds to load changes, we have inaccurate knowledge of this process, glacial isostatic adjustment, the solid Earth response. And if neither's well known, then GRACE is devalued because it requires critically that we understand. So how accurate are the predictions of glacial isostatic adjustment in Antarctica? Well, in order to validate those various different predictions, we need to have some field data, ideally, that can tell us if the various models are correct or not. And here's the complete set of data that we have, about 15 different sites where we have measurements of the bedrock elevation relative to sea level over the last 20,000 years. And so you can see for the vast continent of Antarctica, there is large areas that are not well sampled. And just to give you an indication, this is not Antarctica, by the way, to give you an indication of what we're talking about here, these are Swedish fishing huts that were built several hundred years ago, and they were built on the edge of the water. Now, as you can see, they are no longer out on the edge of the water, and it's not because sea level has fallen in an absolute sense, but because the bedrock has lifted up and taken them away from the sea level. And so if you could date various shells or other features that were on the coastline in this area, you could learn about glacial isostatic adjustment. And in a similar way, you can do something without the Swedish fishing huts in Antarctica. And here's an example data set from some work published a few years ago, where we have measurements of the place of sea level relative to, or the bedrock relative to sea level. And we have some limiting data, so the sea level was below these downward pointing arrows. We have some other limiting data saying the sea level was above here. The circles are telling us that the sea level was about here. And then we have a suite of model predictions that we can test, and we can say, well, the model doesn't fit the data in those locations. But there's a limitation to that, because there's these huge areas of Antarctica where we don't have a good handle of exactly what's going on. We haven't got data that can constrain the models in these areas. And we also are only sampling in most of these places a very limited period of time. We're only sampling the last 7,000 or 8,000, 10,000 years maybe. There's very little constraint early on in the time period when most of the ice was actually changing. But we have another tool, and that's one of my favourite tools, and that's GPS. And using GPS attached to the bedrock in Antarctica, we can measure the present-day response. It's not as powerful as measuring the complete time history of the response to the bedrock, but it tells us something, and we have a lot of bedrock in important places, not everywhere, not yet anyhow, but we have GPS at all of these pink dots and many more actually now around Antarctica, and hopefully more in the future. And so here's an example of what we're talking about. You get to fly to a very beautiful spot, bolt a GPS antenna to a piece of bedrock, deploy a very large power system that tries to run the system through the winter, and day on day, week on week, year on year, we can track the position of the bedrock and measure its position. And we've discovered some really interesting things along the way. This is one site in the Antarctic Peninsula, sort of off towards South America, and these grey dots are the daily positions that we've produced. So there's some scatter here for just variability, but you can see over a period of time that's not going very far, that site, over 1998 to 2002 or thereabouts. It's not going up strongly, it's not going down strongly. Then in 2002, this happened. This is the breakup of the Larsen B ice shelf. This happened over a 6-week period. It catastrophically collapsed and spilling icebergs all into the Weddell Sea. Now, this is floating ice, and as I told you before, floating ice doesn't change sea level. It doesn't weigh down the Earth. It doesn't produce a rebound of its own. But this acts as a plug to the glaciers that are flowing in. Some of these glaciers here that are several kilometres wide, flowing in, and they were being held back to some extent by this ice shelf. And as soon as it broke up, the glaciers sped up by a factor of 2 to 6. And that speed up of ice resulted in an unloading of the solid Earth. And, and that unloading of the solid Earth produced this effect. And so we can see that the site is no longer going along at somewhere near 0 millimetres a year, but is now going up at about 7 or 8 millimetres a year. And that's sustained through that period and even to this day. There are other sites in this area where we predict they've actually risen somewhere more like well over a foot over this period of time. The bedrock has rebounded. And in attempting to explain this, we found something quite interesting. We found that not only is an elastic response, an instant response required, but actually a rapid viscous response. So that the mantle was actually responding very quickly in this area to this unloading event. But taking all of the GPS around Antarctica, we could compare those uplift rates. Most of them weren't doing anything exciting like I just showed you there. They were just going along in a straight line. And so we could compare those to different predictions of uplift. And here we have 2 different predictions that were quite widely used up until a few years ago. Ignoring the little dots on there now, you can just compare the 2 maps. And you can see that those 2 predictions are, are quite different. There's differences in the patterns that are quite substantial. There's a big uplift bulge in this area here, which doesn't really exist in this model over here. This uplift bulge is quite a lot smaller than the one predicted for over here. There's an uplift bulge here in this figure. But most prominently, perhaps, there's subsidence in this model and uplift for most of East Antarctica in this model. So there's significant disagreement between the two models. And the GPS rates are the circles, and they show you that there are significant areas where they're in pretty good agreement with those models. But there are also significant disagreements. So the GPS is not showing rapid uplift in this area anywhere near to the extent of those models predicting, and likewise in this model over here. They just were not showing the level of uplift that the models were predicting. And so this suggests that the models of glacial isostatic adjustment that were being applied to GRACE were not really fit for purpose. And the results of GRACE for ice mass change and its contribution to sea level would not be accurate with these models being applied. So we set out to produce a new model, an improved model, one that would be fit for purpose. And so working here with colleagues at Durham University, Mike Bentley and Pippa Whitehouse and Glenn Milne now in the University of Ottawa, we worked on producing a new model. And Eric Ivans here in the top was independently working on a new model. So that was great, in that we had two groups who were actually independently working and working to improve things. So how do you create a new model of glacial isostatic adjustment? Well, the first step is to create a new ice sheet model, because you want to know the load change with time, how much ice is where and how has that changed. And so Pippa Whitehouse produced a whole series of time snaps of reconstructions of the Antarctic ice sheet, attempting to fit the ice elevation constraints that we do have at the little nunataks, the little rock outcrops that pop out in the middle of Antarctica. Where we know that the ice was at this elevation at this time, or it was below this elevation at this time. Or areas in the interior where we have ice cores, where we know that accumulation has increased over a period of time. And so all of those data provide some sort of constraint. So the grayscale here in these plots is the ice elevation, the modelled ice elevation, and the symbols tell us about the fit to the data that we do have. You can see the data is very sparse. There's only about 25 or 30 points at the last glacial maximum 20,000 years ago. But we can see that in most places, the colour of those symbols is white or very light, suggesting that we're within a few tens of metres, maybe 100 metres of the actual data, or we're at least not in disagreement with the data. There are a few places where we are in disagreement, and it's not entirely clear why that is, and there's room for improvement. And then we go forward in time towards the present day. And so at 15,000 years, we have a lot less data to constrain the models. 10,000 years, we have about the same amount. Some sites that don't fit well, other sites that fit very well. Through to 5,000 years before present, where we're fitting pretty well. And then we, of course, reach the present day. So then we have an ice sheet model, and we've got some confidence of it, and perhaps more importantly, we've got some confidence on the error associated with it. We can produce a whole series of models that are self-consistent, each one, that give us a suite of predictions for how the ice sheet has changed with time. And then we want to tune the solid Earth. How does the solid Earth respond? Well, we don't really know that perfectly, in fact, a long way from perfectly. So we tune our model, and we're going to use relative sea level data, those data that I showed you before around the coastline of Antarctica. And they can be useful in tuning our model. Now we're going to adopt a very simple model of the Earth. We're going to adopt a 3-layer model. And here we have a lithosphere, an outer shell, if you like, of the Earth, which is purely elastic. And we're going to tune the thickness of that outer layer. We're going to look at the upper mantle. We're going to vary the thickness of the upper mantle below it and how viscous it is, which is a function of how quickly it responds to load changes. And then below that, a lower mantle, and we're going to vary its effective viscosity as well. Now, the solid Earth doesn't look like this. This is very much a simplified picture, and it's something that we're continuing to work on, and my colleagues are particularly working on hard at the moment, is actually producing more realism in these models. But nonetheless, we thought we could make some significant headway into this problem. And so by tuning the models against the relative sea level data, this is a series of plots of the fit of these different models, dozens of variations of the different models to these relative sea level data. And so black is a good fit and white is a bad fit. And here we have different elastic thicknesses of the lithosphere. 71 kilometres, 96 kilometres, 120 kilometres. These are just ballpark estimates. And then on the vertical axis, we've got lower mantle viscosity and upper mantle viscosity. And without going into the detail, we see here that this is a preferred option of a thick elastic lithosphere and a lower mantle viscosity of about 10 by 10 to the 21 Pascal seconds and 1 by the 10 to the 21 Pascal seconds for the upper mantle. I guess the details of that don't matter as much, but what does matter is that we had some ability to be able to constrain and tune how the solid Earth responds to ice load changes. But then we can also compare that final prediction with the ice model and the solid Earth model to an independent data set, to our GPS data set, which hadn't been involved in the whole process. And I won't show you these figures, but these are the summary statistics for previous models. So that 5 millimetres a year was the fit of the model to the data. So there's quite a lot of disagreement there. Another model, 4.9 millimetres a year. And our new model, by no means perfect, but about a 50% improvement, 2.9 millimetres a year. So our model was fitting the independent GPS data, uplift data, significantly better. And then we had a model. In fact, we had a whole suite of models because we had a whole suite of ice histories and a small selection of Earth models as well. And so we could apply them all to GRACE. And we took our best one, and that's what I'm going to show you now, and that result was published in the journal Nature in 2012 as well. And this is a map of our estimates of the rates of change over time. And so here we have the browns are mass loss, the yellows are significant mass loss, so West Antarctica losing significant amounts of mass, the Antarctic Peninsula losing mass, particularly following that breakup of that ice shelf I showed you the animation of. And East Antarctica, possibly driven by recent accumulation events gaining mass quite considerably. But the cold interior and high East Antarctica not changing very much, and that's exactly what we'd expect because the amount of accumulation in that area is very small. More recently, we produced an updated time series. This is an example of that, where we see that for all of Antarctica, we see a rate of change of about 60 gigatons a year, and the hint of an acceleration in that change from our data. So here's the mess that I showed you before, and the blue lines, remember, are the GRACE estimates. So where does our estimate fit? Well, it fits in about there. At the lower end of the contribution to sea level. So we were suggesting that GRACE was predicting a much smaller contribution of Antarctica to sea level than some of the other previous estimates using GRACE, and perhaps more in accord with some of the satellite altimetry measurements. But with all the other data and model advances, the various other groups who are working on altimetry and input minus output and GRACE, there was a reconciliation reached. So it was no longer a mess, but actually we'd arrived at this reconciled position. So it did seem like it was time to party, because for the first time in history, we pretty much knew what was happening in the great ice sheets of the planet. But not totally time to party. And the reasons that not to party are threefold before I finish. The ice sheet mass loss is accelerating. Here's a recent study that was published just a few months ago, where we see all of Antarctica, and you can see where you could draw different lines through this particular figure. You could say it was going nowhere, and then it started to lose mass quite dramatically around 2006. You could say it's been accelerating over that entire period. It's certainly been losing mass. But if we look at West Antarctica, then there's no ambiguity here. West Antarctica is losing mass, and it's losing mass increasingly with time. And the second reason why it's not to party is that some of that mass change may be irreversible, in that we may be too late to stop that which has already started. If we return to this ice cube, if moments before this photograph was taken, someone had a blowtorch on these ice cubes, then for the period of this photograph and for some time afterwards, these ice cubes would be responding to that blowtorch, even though it was no longer applied to them. And so it is with the Antarctic ice sheet, in that it is still responding to forcings in the past, changes in forcing in the past. But perhaps more pertinently, the forcings and the changes that are going on now may well persist well into the future. And there's a solid theory behind this, which is known as the marine ice sheet instability. This is a figure showing a normal configuration. Ice accumulates onto the ice sheet. It slowly flows across the grounding line where it comes afloat. The ice shelf melts or carves off an iceberg, and it's all very much in balance. So what goes in balances what goes out. If you get warm water into the ice, into the cavity beneath the ice shelf, you can start to melt the ice shelf. And that produces a thinning of the ice sheet. And so while and as the ice sheet thins, in a configuration where the bedrock slopes backwards into the interior of the ice sheet, the thickness of the ice that's going across the grounding line and becoming afloat is getting larger and larger and larger. The input of the snowfall is staying the same or even getting slightly smaller. So we have a situation where the discharge is getting larger, the input is getting smaller perhaps or staying the same, and we get an increasing imbalance. As you get an increasing imbalance, the ice sheet retreats further, and it retreats further, and it retreats further until it finds a stable configuration. And so the theory does suggest that when a glacier is in one of these unstable configurations on a reverse sloping bed, so as the bedrock gets deeper into the interior, if it's thinning, then once it starts thinning, even if the warm water is turned off, it cannot stop very easily and may well completely deglaciate. And so this is the situation in West Antarctica, where we see that the fringe of the Antarctic ice sheet is coming around here, and then when we have the bedrock is about 1 kilometre deep around the edge of Antarctica, but we see these deepening patches where it's 2 kilometres, 3 kilometres deep in the interior of the ice sheet. We have an instability configuration, and yet we have an ice sheet that is thinning rapidly in these areas, and it is now believed that this is irreversible. And here's a study of different measurement types, a bit like the reconciled estimate that we had, in fact very much like it, but only on the regional scale. And it's studying the glaciers that are in the red box there on the map. And so you can see this not only is the ice losing mass substantially, but it's losing it increasingly over time, and the various measurement approaches are in wonderful agreement. There is no doubt that this ice sheet is retreating. But we can make it worse. 93% of the warming that goes on in the planet is going into the oceans. Only 0.2% is going into the Antarctic ice sheet. So global warming has very little direct effect on Antarctica. Antarctica is a very cold place, it's a very white place. A lot of the energy reflects out into space. But the ocean is in contact with Antarctica. And here we have warm water coming up onto the continental shelf and initiating that melting of the ice sheet at perhaps an ever-increasing rate. And perhaps really concerningly is this vast area of East Antarctica where we have a very similar unstable configuration. So even if West Antarctica is on the way now, well, East Antarctica is not showing substantial signs of change. There's some hints, but it's showing not substantial signs of change. But if it does, then it too can completely deglaciate through this unstable configuration. And just a few months ago, some of my colleagues in Australia reported not only is there a pathway for warm water to get to the base of one of these glaciers that is at the front of one of these unstable areas, but there is actually warm water at the base of one of those glaciers. And so we may be in the early stages of something we wouldn't want to happen, because these vast basins hold many metres of sea level. The IPCC, the Intergovernmental Panel on Climate Change, in their climate reports suggested their upper bound on sea level for the 2100 would be about 1 metre. But they had a footnote, which was a somewhat troubling footnote, in that if the West Antarctic ice sheet deglaciated, then that would not necessarily be an upper bound. And so we may be entering a world where 1 metre of sea level change may just be the starting point. So we can make it worse, but we can choose to not make it worse. And with that somewhat sobering thought, I'll thank you very much.
So that was a brilliant lecture. It was great to hear the science, but it was also wonderful to see it being delivered in such a clear way. Matt, we've got to both stay close to the lectern because we've got to make sure that the camera can see us both. We're going to have a question and answer session now. We've got about 10 minutes roughly. And if you would like to ask a question, if you could put your hand up, and if you could, when you stand up and when the microphone gets to you, if you could say who you are and where you're from, and then ask your question fairly succinctly, then we'll be able to have more questions. So, any questions? There's one down here at the front, the gentleman in the blue, and then a gentleman in the middle after that.
Thank you very much, Julian O'Halloran. I'm writer and broadcaster. Given everything you've told us tonight and all that you have learned during your career on this, how tempted would you be to raise that 1 metre upper limit suggested by the IPCC, and if so, by how much? Because there are respectable bodies in the world which are talking about, you know, up to 2 meters, that kind of thing. You know, not fly-by-night people, really serious organizations.
Yeah, it's a good question, and it's not one that I'm well qualified to answer. The baseline figure, the 1 metre, may not necessarily be where we get to. If we forget about a destabilised Antarctica, in that if there is serious mitigation and reduction of carbon going into the atmosphere, then the forecast is somewhere more like 0.4 of a metre or 0.6 of a metre. That's still bad news for the Pacific Islands and people who live in Bangladesh, but it's not as bad news. The science is most definitely out, unfortunately, in terms of how quickly West Antarctica could deglaciate. There are models that suggest it could be 200 years for the total volume of, say, 4 metres of sea level. It could be 1,000 years. And so that's an unsatisfactory answer to the public, I know, because we really have to be able to nail that down. We have to know exactly what that contribution is now that we think that actually it has entered a destable phase. And so that's why we need to get continue with the satellite measurements, but also continue to get out into the deep field. And I know the British Antarctic Survey and some of the US colleagues are actually working very extensively with UK colleagues, myself as well, in those areas, those critical areas, in order to understand exactly what's going on and what our risk is. But it's sort of watch this space, which is sort of unsatisfactory, but we don't know.
Gentleman in the middle.
Hello. Yes, a metre of sea level rise may not sound too bad, but one little sum I have done is that if it rises by a metre, it will take a strip of land 10 kilometres wide off the whole of the east coast of the United States. So that would have a significant impact. It will also flood 25 million, where 25 million people live in China and a similar number in Bangladesh. So it certainly isn't something we should be complacent about. But you say we can choose not to make it worse. Presumably, you're suggesting if we choose to limit the amount of burning of fossil fuels, then it'll not make it worse. But at the moment, we aren't really doing very much about burning less fossil fuels. We've developed renewables over the last 35 years by a bit. We need to develop them 12 times faster in the next 35 years by 2050. So what can we do to get the world to do something about it?
Yes, well, you'd recognise, of course, that I'm living in Australia now, where our country is perhaps the worst offender in the developed world at the moment in terms of not addressing this issue. And so most definitely we have to reduce carbon emissions, and that may well save the East Antarctic ice sheet. We really know almost nothing about those big areas of East Antarctica, almost nothing. Some of them have hardly been visited over the ground. They're some of the most remote places on Earth. It really is a desperately bad situation that we are in, that we know so little about some parts of Antarctica. But, I mean, I guess speaking out of turn, we have to look at the renewable energy sources. And I personally think that nuclear needs to be on the table. In that, I know that Britain is moving in that direction. Australia has never considered that, despite having a lot of uranium in the ground. But I'm led to believe that new generation, fourth generation nuclear is significantly, possibly more effective. But I'm really stepping outside my expertise levels there. Yeah, but I agree with your sentiment.
More questions? Yes, so we got one there in the pink shirt in the middle, gentleman in the pink shirt, and then this lady over here in blue cardigan.
Hi there. My name's Ben Johnson. I work in climate change abatement. I had a query around the increasing or the loss of ice leading to an increased height of the seabed elsewhere, and whether that has any impact on the sort of sea levels elsewhere on the planet, and perhaps more habitable places.
Yeah, so the ocean bed is subsiding at the present because the mantle material is still moving towards the continents, particularly North America. And so when they're measuring sea levels from space, for instance, they have to account for that, because otherwise they might be actually measuring a value that's too low by, as it turns out, about 0.3 millimetres a year. So it's a small number, but over the whole vast oceans, that matters. I don't think it's going to change anyone's lives particularly, but it's an important detail that scientists have had to be on top of. Yeah.
Hi, I'm Natalie. I'm from Wallacea, which is a crowdfunding platform for science. You mentioned that there aren't very many studies in East Antarctica, and we know very little. What kind of studies would you like to see happening in East Antarctica? Well,
it'd be nice to know, for instance, what happened at the last time that Antarctica deglaciated substantially, which is known as the last interglacial, about 120,000 years ago or something. How far did East Antarctica go back into its interior? How vulnerable, that would be a good indicator of how vulnerable we actually are in those areas. And I'd say we don't know that information at all at the moment. It would be very important to make continuous long-term measurements of ocean temperature at the front of the key outlet glaciers. And it would be good to know what the properties at the base of the glaciers are like, and that requires ground work, and quite substantial groundwork, in order to measuring seismic measurements, radar measurements, perhaps GPS measurements looking at flow variation, and those sorts of things, as well as a continuation of these wonderful satellite tools that allow us to look at things that are going on from above as well.
Okay, more questions. So we're flooding in now. So there's one here at the front, this gentleman, and then there's a lady in the middle right next to you. There we go.
I'm Keith Moffat from Cambridge University. Do we have a reliable picture of what Antarctica would look like, what the contours of the rock underneath the ice are? I mean, if there were no ice at all there, what would the continent look like?
Yes, well, present day, if you stripped off all the ice, it would look like this. And eventually, that bedrock would rise up by several hundreds of metres. But you can see that would give you a broad picture of what it would look like. And you'd see there's a whole series of islands and archipelagos in West Antarctica. But unlike was thought for many years, there's actually significant areas of Antarctica that would be filled in with water. East Antarctica would be filled in with water as well.
Hi.
Yes.
My name's Rianne from Leeds University. I was wondering how much value you would ascribe to looking further back in Antarctica's glacial history, and whether you think that has how much use you think that has for understanding future change.
Well, I think it's really important to know what Antarctica looked like when carbon dioxide levels got to the same level that we have now, which is about 5 million years ago, I think. Sea levels, I think, are predicted to be 5 to 20 metres higher at that period of time. It would be nice to know exactly how much of Antarctica wasn't there at that point. But most recently, so for the last 20,000 years, we really need to know, if we're going to maximise the value of this wonderful GRACE satellite mission, we really need to know a lot more about where the ice was and how that changed with time, because we've got some great measurements at various different places, but there are huge areas of Antarctica we just really don't know how much thicker. Was it 500 metres thicker ice at the last glacial maximum? Was it no thicker? And when did that change? Those sorts of measurements, we need our geologist colleagues to get out and make some more measurements and develop new techniques actually probably as well.
Okay, I'm just going to take two more questions. One over there on the left, gentleman over there, and there was another one somewhere, I thought. Yes, just down here. Oh, sorry, this gentleman here with the blue shirt. Thank you.
Hello.
Hello.
Can you hear me? I'm not an earth scientist, so excuse the naivety of this question, but physics was my background way back. I'm interested in this concept of grounded ice. Going back to a long, long time ago, an iceberg, you see a bit of it above the surface and 9/10 of it is below the surface. Isn't that an issue as to how you actually decide when an ice becomes grounded and not grounded in terms of the topography of the land underneath? And is there a correction factor around that? Does it depend upon the actual topography of the solid mass underneath the ice?
Yeah, and you've seized on a really important point in that the melting of the ice sheet, if you think of a big bit of ice that's grounded on the bedrock, and it's thick enough for it to be grounded on the bedrock, even though it's in touch with the ocean, directly in touch with the ocean, but it's sitting on top of the bedrock. Now, as that glacier thins and thins and thins, eventually it'll get to a point where it actually comes afloat. Okay, and from then on, it's not adding to sea level at all. So that has to be considered. Now, one of the great things about GRACE is it actually measures total mass change. So it doesn't measure the rest of that thinning beyond. But the other techniques need to take that into consideration, absolutely.
Yeah, yes, last question.
I'm still quite puzzled about the previous 5 million years, or however long ago it was, when the present CO2 concentration existed. Is it going to be possible to get the CO2 back down to 250 or something like that in time to prevent that happening? And yes. the other part, since the last interglacial, what was the peak rate of melting and rate of sea rise historically in the data?
Yes. Okay. Well, I'll answer the second part first. There was there is believed to have been a tremendous pulse of meltwater during the last 20,000 years at about 15,000 years ago. And sea levels probably rose then about 10 times what they're rising today, about 30 millimetres a year. Sea levels rose 15 metres or so over 500 years or something like that. So the Earth system at various points in its history has shown an ability to very much faster rise sea levels. Now, that doesn't mean that it's in the configuration where it can do that now. We don't know. The first question is well outside of my domain, but it is one that we must get on top of because, let's make it blunt, sacrifices are required, probably, almost certainly. And our Western lifestyles are probably right at the top of the list in what needs to be done, unless there's a major, major breakthrough in the next 6 months in energy production.
Well, Matt, thank you very much indeed. This has been an incredibly good lecture, an incredibly interesting lecture from a scientific point of view, and an incredibly important lecture, so very important for society. Before you go, there's a little bit of something to remind us of the event, and it's a three-part something. So the first thing is a scroll from the Royal Society to honour the fact that you've given this great lecture and this award, and we're enormously grateful for your research, but also for explaining to us today so eloquently. So thank you very much indeed. And the second thing is a medal, a Kavli medal, in honour of your research as well. So fantastic, well done. Thank you. And then there's this check. Thank you very much. Big round of applause. Thank you. Thank you. It was really good. Fantastic.